let's see here. Okay. Okie dokie. So, we're going to look through wide area net solutions. Wide area nets, from the point of view of this class, are kind of an interesting thing. They're the only technology we look at that really and truly most enterprises are not going to build on their own. Unless you work for a government, like a national government, maybe a really big multinational, you're not going to build a wide area net. You're going to pay a carrier to move your traffic. When we looked at PANs, of course, we were looking at stuff that you can implement inside the company easily. LANs, we've talked about. We'll spend a lot of time with LANs here in a little bit. You know, that's commonly implemented on private equipment. MANs can be, typically are not, but can be implemented privately. Wide area nets you can't. It's simply prohibitive. You're talking about, by definition, networks that span a country or even span the globe. So that's, you know, a hugely different problem. And it's made some real changes in the last 2 or 3 years. This is the standard wisdom is up in the air right now, or being rewritten right now. Excuse me, I'm dry this morning. So anyway, we're going to kind of look through that. I'm going to do an overview. You know, with homecoming and everything, I didn't assign the reading ahead, so I'm going to go ahead and do an overview. I'll get you to read the chapter for Wednesday. We're going to dig under the hood on cellular, somewhat dig under the hood on satellite a little bit, and kind of look at it. Today, we're just going to kind of see what's waiting for us for those 2 days. As I said, as you go through and look at, you know, a PAN or LAN or metropolitan area net, they're doable on an individual basis by an enterprise. When you start talking about wide area net, you're going to pay somebody who has already built this network. So why is it affordable for them? Because they can charge you part of their costs. They take their costs and spread it across their entire customer base. So they can afford to do things that we would never be able to do on our own. Same thing applies to hardline networks. It's just we don't have to build the hardline network when we do it either. The difference in wireless in the wide area net is really what you're paying for is wireless access to somebody else's wired network, wired fiber, you know, same thing, a hard media network. The other option is satellite, which we're going to look at. Satellite is attractive and in some cases is the only solution. There are some problems with it, so we're going to kind of think through those. Remember that what we're talking about here is how we deliver data. It's almost the same kind of discussion as we had with antennas. Where do we need to deliver data, and what do we need to do that by radio? So that's really where I'm kind of pointing the discussion in this. The major WAN technology fall into 2 primary categories: cellular carrier systems. I don't say cellular telephone anymore. Depending on which carrier you look at, it may be based in telephone technology. That's pretty rapidly changing across all carriers. most of the major carriers now have actually moved off of being a telephone network and are a pure data network that, oh, by the way, happens to do voice as part of their package. We're going to talk about the difference where that crops up a little later. Also, satellite-based systems. Satellite systems are the only feasible solution in some cases. You know, cellular carrier systems are broadly available. They're available on all the continents except Antarctica, and I wouldn't swear that that wasn't the case, although I'd kind of bet on it at this point. Capabilities of the cellular network are going to vary right now. You know, obviously, the developed world, Europe, the Middle East, a good bit of the Asia-Pacific rim, good chunk of South America, North America, all pretty well built out and relatively near the front on the deploying of technologies. You get further away from development and you know, you may be dealing with older systems. So we're going to kind of look at what some of those are. You get way back, though, and satellite's really the only way to go. If you are doing something, I had a customer several years ago that was a big paper company, and they would buy literally tens of thousands of acres in the middle of a forest somewhere and then set up shop for 2 years. Nobody's going to build infrastructure using hard media, you know, 200 miles back for one customer. It's just not going to happen. And so in those cases, the only solution was to use satellite-based systems. You get into situations like ships, you know, little tough to string fiber to a ship, particularly if it decides to move. So there are cases where you have to use satellite systems. I'm not really looking so much at the moving systems like ships and things like that. Those are kind of obvious. What I'm looking at are places where it makes sense to use satellite systems as an alternative to cellular systems. So we'll kind of look at that a little bit. So when we start talking about cellular technology, what we're actually saying is that you have base transceiver systems, radios on a tall tower that service customers, the last mile access, if you will. And physically, their coverage area is circular. When you start serving a lot of customers, the problem you end up with is there's only so much spectrum, and everybody has to share it. And even with the spectrum sharing technologies we've talked about, it's not enough. And so what some smart people did, actually further back than you might think, is they came up with the idea of what we would call the cellular concept. Traditional thinking is that, you know, I need broad coverage, therefore I put up a really tall tower, I use high power, I cover as much area as I can. That's great, but I can only service as many customers as I can subdivide that spectrum that I use over that area. Give you an idea. The old mobile telephone system from the predecessor to the cellular system had 3 channels for metropolitan New York. That included New Jersey, Manhattan, Queens, up into Connecticut, all that. Imagine 3 lines for that whole area now. What cellular does is take that fact that those circular areas are one tower, and that where we put them close together, their areas overlap. So there'll be an area. If I'm standing in the middle of 1 and 4 here, and I'll explain what 1 and 4 are in a minute, there's an area in here where I'm going to hear both 1 and 4 equally well. We'll come back to that thought in just a second. What we do with cellular is very closely control coverage area. We control power. We actively control power. The intelligence in the network directs the handsets to increase or reduce power as needed. And the cellular systems themselves, the basics you can. And we design the system to accomplish a couple of things. First off, we look at where our users are. As we have more people, we reduce the coverage area. As we have fewer people, we'll make it larger. So we vary our loading based on how big we make these cells. What's a cell? Okay. What these numbers represent are unique frequency ranges. Call them channels, call them spectrum, whatever you want. They're unique. So 1 is a different set of channels, if you will, than 2, than 3. What we do in cellular is build a network where you never have the same channels used adjacent to each other. In 321, you'll go deeper into this. There are formulas for how far away you have to be before you can reuse channel set 1, for example, and how many different channel sets you need. And so there's a fair amount that goes into designing this. But the fundamental idea is that I reuse those frequencies. And so I can design coverage based on how much capacity is in a cell rather than how far I can push one cell. So, and that's a key piece. If I build this tower very tall, very high power, I may cover a big area, but once I've saturated the capacity of that cell, I'm through. That's all I can do with that. Whereas if I control the coverage, make it smaller, I can use that to cover this area and then take those same frequencies and reuse them over here to cover more area. Okay? Like I said, 321 goes a lot further into that, but that's the basic idea behind it. Now, the area of overlap in here is what allows users to move. And we've actually kind of hit on this in here. I just didn't use these terms. What you're doing, if I'm a user that starts out near Tower 1 and I'm walking towards Tower 4, what's happening with my signal to Tower 1 as I walk away? It's going down. What's happening to my signal from Tower 4? It's increasing. The network intelligence, if you will, behind this keeps track of how my mobile is received by both of those towers. And it's going to be able to determine that trend. At some point, it's going to make the decision that I'm in this area of overlap where I'm hearing him about equally well, and, you know, he's been going this direction, so we probably ought to change him to channel 4 instead of channel 1. I'm going to say channel because it's easier. Channel 4 instead of channel 1 before he gets so far gone that we can't reliably receive channel 1. And so the stations, these two will cooperate, and it depends on the technology is exactly how that works. But they instruct the mobile to change channels and switch from 1 to 4. That process is called handoff. And it is, you'll run into it in a surprising number of technologies. You're used to it in your commercial cellular telephone. We're going to look at precisely this process when we look at 802.11 LANs, because they do the same thing. That's what, when you hear the term mobility for cellular systems, that's what you're talking about. It's not just the fact that you can move, it's the fact that you can move between coverage areas and not lose your, well, keep a strong signal, yes, but not lose existing connections. Okay, and that's a real trick. Okay, so with cellular, what you're looking at is how I move between a designed coverage cell system. Now we've, of course, this started off in the 80s as cellular telephone, actually in the 70s, but it didn't really get going until the 80s as cellular telephone. And we've gone through several generations of technology on this. We're actually rolling out fourth generation now, and that's actually how we talk about the different technologies. You've heard the terms 1G, 2G, 2.5G, all that stuff. 3G is the big one everybody knew. Everybody uses, you hear a lot of people use the term 3G and they don't have a clue what they're talking about. They've just heard it. So we're going to look at them a little close. The original cellular system, first generation, was something called AMPS. It's Advanced Mobile Phone System. This was purely voice telephony, used analog voice over analog FM modulation, channelized. The signaling, the part of where I go off hook and I dial a number and tell the network where I want the call to go and all that, that was always digital in cellular and our implementations of cellular. But that was really the only data capability you had. You could do effectively a modem kind of thing, but it was 9.6 kilobits, which was appropriate because this was 5 years before anybody was using the World Wide Web and before Al Gore reinvented the internet to be commercial. This wasn't a big deal. Okay. As we moved forward, what happened is as they built out the network, each call actually used two channels, a downlink channel, which came from the cell base station towards the handset, and one that went from the handset towards the base station. That's why you could talk in full duplex. As more and more users came on, and as we got more cells going, demand, the number of users per cell, outstripped capacity. And so started moving towards more capable technologies in terms of the number of users that we could put in a single cell. And we were starting to see demand for text messaging, for email style messaging. I want to be able to move small amounts of data. Okay. And so we ended up with the second generation systems, 2G systems, and there were actually 3 different technologies, all interesting in their own right. Again, you'll look at 321, 322. GSM, and Global System for Mobile, TDMA, which is time division multiplexing, and CDMA, we've talked about code division multiplexing. All of those took the analog channels, coded the voice, and then moved coded voice across a digital carrier. It was still circuit switched. I still thought of it as a dedicated channel. It's just I'd set it up so I could put more users on the same frequency. For example, the first TDMA solution took each voice channel and divided it into 3 time slots. So I tripled network capacity just doing that. I could handle 3 users in the same spectrum that I'd handled 1 before. A little later, they doubled that again and got 6 users in that same space. Similarly, CDMA, through a different process, did the same thing. We were able to allow more users in there because we were coding voice, treating it as circuit switched, and then sharing it digitally. It just simply works better and is more efficient than using analog channel combinations. GSM at the time was also circuit switched. It was coded. It just simply did that spectrum sharing in a different manner. It worked well. Notice what happened with our data rate. We jumped up a little bit, got to 14.4. Still, we're going to use this for a lot. And in fact, most customers didn't use any of the data capability. They just used the voice. Okay. So that was 2G. In this time period is when you started getting lots of people using the internet. More and more people ended up with email systems, email accounts. And there was more demand for doing data from my phone. I wasn't trying to browse the web, although some people did, and there were, as your book told you about, there were cut-down versions of web browsers and stuff that were text-only and things like that. Your book makes more out of it than I ever saw, to be perfectly honest. But the demand, you can't argue that the demand for pure data usage of this network that was not moving the human voice, was on the increase. Smart people do these things, and they saw the trend. So what we ended up with was something called 2.5G, which was still data. We still used the same voice coding, but we made a couple of changes. First off, we moved from a circuit switch where I dedicate bandwidth per call to a packet switch network like you're used to with Ethernet. You know, all users on a circuit switch network, I give each user part of the network all of the time. I dedicate bandwidth to them for the duration of a call. In a packet switch network, you give each user all of the network part of the time, and you just let everybody use it, and you switch between users very quickly. There are lots of technologies for doing it, CDMA, all of that. That was a key switch. Second is we actually rolled out data-only uses at useful bandwidth. You know, 114K, 144K. Edge was the real fast one, 384 kilobits. At the time, that was a pretty speedy connection. So this was slower than wired connections, but usefully fast, given the time. This would seem incredibly slow to us now for anything other than text messaging. But for data purposes, these were actually fairly competitive data rates. Okay? And for the first time, this is way before 802.11, wireless LAN. For the first time, I could actually do real data applications walking around. Pretty neat trick. Okay, so we move along. We all know what happens once the internet jumped out and everybody started doing web pages and everybody had an email address. You started getting social media coming along, things like that. Same thing happens in any kind of application development. The demand for data goes up. I'm doing more with it. I'm doing bigger things with it. I need more bandwidth. And this is basically the trend you see all the time. So the next step was to go to 3G. And this would have been 12 years ago, thereabouts. What happened in 3G is we kept digital voice. We designed these from the outset to be packet switched. Remember, at 2.5G, we basically took a circuit switch network and adapted it to be packet switch. Here we designed networks from the very beginning to be packet switched, and we built in significant data capability. This is still what the majority of the network is this technology. Depending on the carrier, you're using different flavors of it, but they all accomplish basically the same thing. What it is not is very IP friendly. This is not an IP network. And each carrier, I shouldn't say each carrier, although it does sort of break down that way. Each of these technologies deals with the network differently and deals with the connection to a packet, to an IP network differently. Okay. What was needed was a way to get high-speed data to mobile devices that was IP aware. You know, you guys have been studying this a long time. It's an IP world. You know, nobody's going to argue that. As IP6 takes hold, it becomes even more, because now we don't even have all the rigmarole of trying to increase how we can use our address space. We've got enough address space in IP6 to, you know, address everything you want. There are more IP6 addresses than there are grains of sand on Earth. That's a figure that kind of blew me away. So what that means is we've erased these hard edge boundaries. I no longer really care what network my device uses, but I do care that it can always get on a network. Part of the way you saw this, and this happened in 3G particularly, was dual mode phones. You'd see one that could speak GSM here, and then as I went somewhere else, I could speak CDMA, for example. There are phones, if you're an iPhone user or a Droid or one of those, you know, you use them on IP 802.11 networks when you're within range. When you're not, it uses the carrier network. Now the problem is your sessions don't survive that. So if I have an open session to a server somewhere pulling data. As I cross that network boundary and I go to a different IP network, I have to reset up all of those connections. Now, honestly, for most things, you're not even going to notice it happening. For some applications, it's a big deal, and for carriers, it's a big deal. That's a huge load to make that change. Okay. What 4G does is move everything towards an IP basis. It also vastly increases speed. I mean, look what's going on here. You know, the typical desktop now runs at 100 megabits. I'm running a lot slower than that in all of the 3G technologies, although some of them now have been tweaked to where you can get a better rate. Look what we're doing with LTE. A gigabit? That's useful bandwidth. And it's big enough bandwidth that I can actually use this as an infrastructure piece for the enterprise. I'm no longer talking about doing text messaging to a single user here. I've got enough bandwidth that I can actually use this as a backbone piece. Our university primary uplink is slower than 300 megabits. And we have pretty good uplink. Now, we talked about standards. ITU, the International Telecommunications Union, actually argued that LTE's actually been around for a while, just not in its current form. And they argued that LTE, and they include WiMAX in this as a 4G technology, weren't really 4G. And they did some maneuvering around and changed a few things, and they finally decided for the practical purposes they are. So we'll refer to them as 4G. On the horizon, what you're seeing are what are true 4G systems. What are these? These are basically the kind of networks you look at building, you know, for wired networks. It's just we're doing them wirelessly. And it's only the last mile that's the wireless piece. So in other words, what you're going to end up with is just a really nice IP network that you happen to get at wirelessly. We're going to come back and visit that thought when we jump into our look at 802.11, because the same thing applies there. So anyway, this is where we are right now. 4G has started to be deployed. LTE you're starting to see crop up. You actually see it crop up here in Murray some. If you're on AT&T, you see LTE in place. It's still primarily a metropolitan area piece. AT&T is kind of out in front on getting it rolled out broadly. It seems to me, I haven't really studied that closely, but it kind of, when I talk to people, most of the ones who see LTE actively used are AT&T outside of the city limit, big city limits. What you're going to see is that adopted as the overall network internationally. Okay, think about what we've been talking about. Here is a very capable bandwidth network that doesn't see the world as a single carrier. It sees it as an IP network with divisions. Okay, which means I can set up sessions and let them stay. I don't have, it's not my ability to support connections over boundaries is no longer dependent on my layer 2 implementation in the WAN. Okay, that's the key thing that's going on with LTE and 4G. Okay. Cellular has the advantage that it is broadly available, it's affordable commercially. You know, I mean, you guys are walking around with LTE now, some of you probably. I don't have to worry about building my wide area network. I do have to be concerned with my security. I'm going to leave most of that for Wesley Spencer to deal with. But really our problems are not vastly different than any other wide area net at that point. You know, we've got an IP network. Here's the trusted network. Here's the untrusted network. How do I manage that gateway between them? We're in familiar territory. So, one of the things we'll talk about Wednesday when we dig a little further into this are practical practical reasons you would use this and practical applications instead of using a more traditional fiber or carrier-based VP or VLAN-based network. Okay, for those places where you can't get cellular or where you have a reason to do something else, you have satellite technology. And this, of course, has been around for a while. We've had satellite communication for, call it 50 years commercially. Current implementations of satellite wide area net basically use 4 bands, 4 frequency bands. L-band, you can read them. These are those radar sub-bands we talked about. They're all in the gigahertz range. But notice the range. I mean, we start at 1.5 gig. That's below 802.11 by about a gigahertz. And we'll go up to 31 gig. That raises some issues. First off, what happens to path loss as you go up in frequency? It goes up. And it goes up with the log of frequency times 20. So how would you characterize the loss at L band versus the loss at Ka band? It's going to be vastly different. Okay. Also, we're talking about something that's not 10 or 20 miles. We're depending on the orbit. This is anywhere from a couple of 100 miles out to 22,000 miles. Do the math on path loss for 22,000 miles. Basically, you can characterize orbits in 4 ranges. Low Earth orbiters are pretty close, by definition. In fact, if you want to compare them, low Earth orbiters are down in the 200-mile range, down in here. One of the things you get into a satellite is it's a long path. Now, 200 miles isn't all that long. But radio waves travel at the speed of light. Okay? So it takes a finite amount of time for me to transmit that signal to cross 200 miles before you hear it. At 200 miles, you're looking at 20 to 40 milliseconds. I'm going to use telephone as an analogy because it makes this a little more approachable for you, for us mere humans. We'll talk about the data view of this in just a second. Most humans can't detect 10 to 20 milliseconds of delay unless you're listening to yourself on headphones. You could hear 10 to 20 milliseconds maybe. You get up to 40 or 50 milliseconds, and it's beginning to get noticeable. It's like being in a big concert hall, that kind of echo you hear in a big hall. That's 30, 40 milliseconds. Okay? Still doable. We don't mind. Humans get concerned about this when latency, that's that delay between transmit and receive from the time I say something until the time you hear it. When latency gets above 100 milliseconds, we start fundamentally changing the way we work. We go from a full duplex conversation, you don't think anything about it. If you're standing around with a bunch of folks, 2 or 3 people talking at once, you don't think anything about overlapping or anything like that because you can hear it all. As you insert more and more and more delay in that, we don't like it much. And in fact, it's one of the key problems with voice over IP is controlling latency. Okay. Realize that a good portion of the data in anybody's wide area net nowadays is voice over IP. So, and there's already some irreducible latency because it takes time for me to code that audio and transmit it. So I'm already building some latency in just using voice over IP. The problem is, once we get above about 100 milliseconds, we stop doing the two-way talking thing and it turns into CB radio, walkie-talkie kind of thing. I'm going to talk and then I'm going to make a big pause and then you'll talk. we slow down. We also change the amount of content that we put in conversation. It's less efficient. So low Earth orbiters, no problem. We're going to see how these things all tie together. Medium Earth orbiters have latencies depending on their altitude of 50 to about 150 milliseconds. So depending on what you're doing in MEOs, you're getting into that range where it's a problem. Iridium, the satellite telephone system that everybody's heard, and some of the others, run in these kind of orbits. Okay? High Earth orbiters take the upper end of medium Earth orbiters and move it further out. You actually don't see a lot of commercial use of this. These are used in, if you work for big scientific organizations, they'll use these. The problem with high Earth orbiters, anything that is below geosynchronous, the satellite appears to move across the sky. As it gets further away, as we make this orbit higher and higher, what happens to path loss? It goes up, so I've got to make my antennas higher gain. What am I doing to the pattern on my antenna as I increase gain? I'm making it smaller and smaller and smaller. So I'm going to have to start pointing these antennas. As I get the orbits higher and higher, I'm going to have to point more and more energy, focus energy more and more and more. And I'm going to have to point that more carefully at the satellite. By the time you get up to high Earth orbit, where it's still moving, I've got to track the satellite across the sky. Low Earth orbiters you can use with an Omni antenna. Medium Earth orbiters, probably you can. It may be ugly. If you've ever seen the satellite phones, they've got those huge antennas on. That's what's going on. You're putting a lot of gain up there. Geosync is way out there, but apparently it doesn't move. What's going on is as you move further and further out, of course, you can see more and more and more of the Earth, because it goes from being, something that's all around you. As you move further back, you know how you look at a big tree or a big building, you move further back and you can get it all in your range of view. That's what happens as you move the orbit out. The other thing that happens is the speed, the orbital speed goes up. And once you get to a particularly particular physical point, 22,282 miles, orbital speed and the Earth's rotation are exactly the same. So the satellite is orbiting at the same speed the Earth is turning and apparently stays in the same point in the sky. That's how all of your satellite television and stuff like that works. Okay? I'm sorry? Yeah. Now, so we've got kind of an interesting little thing going on here. We can cover more area as we move the satellite further out, but we make it harder to get a signal to and from the satellite, right? Because we've increased path loss a lot. We change latency, which is a problem for voice now. If you think we don't like 100 or 200 milliseconds, start looking back through some of the protocols that you've heard about. An awful lot of them time out at 100 milliseconds. You can't use them. Perfectly good link, perfectly good signals, it'll time out because it thinks the other end's not there. So we have to rework protocols to use these kind of links. The other, sorry, I took a step off the path here for a second. The other thing we're playing with is what happens to antenna size for the same gain as I move up in frequency. Higher frequency antennas are physically smaller, so I can pack more gain into a smaller antenna. So I've got this kind of balancing act going on. These are very convenient because I don't have to steer the antennas, but to use them, the path loss is so high, I have to use extremely high gain antennas. Good thing I don't have to steer them. The downside is very high latency, and I have that huge path loss. So this is kind of what you get into when you're dealing with choosing satellite technology. You really have to be careful to pick the one you want. Just as an illustration, if we take our free space path loss, and remember we've been dealing with pretty normal systems, our path losses have been 105, maybe 120 dB. Take a look what happens when we're doing 17,500, which is about halfway through this range of frequencies, and a geostationary orbit. 208 dB. Remember that half power is 3 dB. This is a tough problem. We've gotten really good at it. Electronics have gotten extremely capable along this line. And you can actually do these systems in something that you can put in a briefcase. The other side of it, the expense of doing this it varies depending on which system you're using. It varies by bandwidth. There's only so much uplink and downlink bandwidth. There's only so much geography in that orbital, in the orbital mechanics model. I can only put so many satellites out there because I can't put them any closer than I can separate with a ground-based antenna. So if I put them closer than 200 or 300 miles from each other, they're within range, two satellites are within range of one antenna. So there are only so many slots where I can put satellites out. So what you end up with is you have to really consider what you're doing for video. And I didn't put this up on the slide. I do have it on the, or will have it when I post my notes. CTSM up front has done satellite-based emergency response systems. They're systems when all the infrastructure goes down, you can deploy these rapidly, and the way they get their bandwidth is satellite system. They're actually moving to, what do you think, LTE for a lot of them. But to give you an idea, Inmarsat, if you do a prepay thing, in other words, I'm going to pay for bandwidth, basically I can use this amount of bandwidth. I'm guaranteed being able to use it over some period of time. For example, 25 units of bandwidth, and a unit is about a minute of voice. 25 units is $18.50, and you can use it for up to 2 years. Okay, that's $18.50. As you go up, remember that that's 25 minutes of voice traffic, basically, or the data equivalent of that. Probably not going to run a corporation on that kind of capability. So as you go on up, you get to 500 units would be about $370. 5,000 units would be $3,700. The problem with the prepaid plans is that once you use up your bandwidth, they stop your uplink. So, and that might happen in the middle of something you need to have happen. They're good for the kind of service CTSM uses them for, which is when bad things happen, I need to use this system. They're not a good thing to rely on. So you can also have ones that are more familiar looking in terms of bandwidth. So I can look at transferring 120 megabits, for example. To be, let's see, 120 megabits, they'll charge me $780 to move 120 megabits. I can move it any way I want, anytime I want. Once I do that, I've got to buy more space. And it goes on up. There are also annual contracts. They'll typically run $3,000 to $4,000 a year that would allow you up to about 1.5 megabits. So I'll get this posted Wednesday. If you would read the chapter before Wednesday, we're going to dig a little deeper into the cellular application. We're going to dig a little deeper into the satellite technology. So see you Wednesday.